Obviously, the parent function is not much of a parent function if we can't use it to think about other versions of the absolute value function and the absolute value graphs. Right here on the top line of our graphing, we have what's called the general form of the absolute value function. There are three major changes that we typically can make to an absolute value function to move it, reshape it, and adjust it to fit the needs that we have for a particular situation. We can control the number that is in front of the absolute value. That number controls the steepness and the slope of the sides and the direction of the V. We can control the number that's on the inside of the absolute value being subtracted from x. That number controls the left and the right translation of the graph. We can also control the number at the end of the function being added or subtracted, and that's going to control how the graph moves up and down. As we adjust a, h, and k, we will adjust the placement of the absolute value function, moving it into different spots as needed and as necessary. The first one I want to look at is the a. Right now, we are set at the generic parent function. A is 1, there's no multiplication in front. H and K are both 0, there's no left and right translations. All we have is the generic parent function absolute value graph. As I adjust A, you'll notice that the graph gets steeper. That's what we should anticipate is happening. Look at the position of A. A is saying, I want all of this value that you're used to calculating, but I want you to multiply it by 2.8. So certainly both sides of the graph are going to be growing significantly faster than they were previously. Everything that would be created as part of the absolute value function is now growing at a much faster rate. And if I continue doing that, it will continue getting steep. And if I was to zoom in, I could continue getting it steep. And obviously, this slider stops at 10, but we can already see how much steeper it is. The question is, are we able to quantify that change in the steepness? If I go back to the original parent function where a is equal to 1, I can see that right here I'm at the point 0, 0, and right here I'm at the point 2, 2. When I have those two spots, I can see that my slope is 1. That's what we talked about with the parent function, and that's still what's happening here. The moment that I change the steepness, we'll multiply by a factor of 2 instead of by a factor of 1. I'm still at 0, 0. Obviously, multiplying 0 by 2 doesn't change anything. But if I was to go over to 2, I'm now all the way up here at 4. Thinking about that in terms of slope, it's fairly obvious what's happening. This number is redetermining the slopes of the two sides. Now, before you say to yourself, well, yeah, that's all well and good, but what's happening on the left side? Remember that we look at slope going left to right. So if this point is at negative 2, 4, and the point at the bottom is still at 0, 0, that's just a slope of negative 2. And that will work, that logic will work, that principle will hold no matter where I adjust this to. We would anticipate at this point that my slope would be 4. Here's my 0. Here's the point 1, 4. There's my slope of 4. So as you adjust this A number, you are adjusting the steepness of the sides and making these sides have the slopes of whatever you might need them to be. Slope of 7.1, you could change A to 7.1. Now you'll notice that I have very much stayed away from the negatives. What if I made the decision to slide A all the way back into the negatives? Well, fortunately for us, the same exact slope conversation happens, but instead we're going the opposite direction. Remember how we talked in the last video about the fact that the absolute value makes everything positive. If I was to make A negative 2 like it is here, that forces all of the values to go below the axis, not above the axis. I know that whatever I get out of this absolute value is going to be positive. And when I multiply it by a -2, I know that has to end up being negative. So if I'm going to do that and I'm going to go through the trouble of making a negative, I'm getting this graph that's now going the opposite direction. But I've got a point here at 0, 0. I've got a point here at 2, -4. My slope is now -2. And you can imagine that if I was to go this way, then my slope would just be 2, as opposed to this way when the slope is -2. And if I flip it all back and I go to a is 2, you can see the obvious similarities of where I was previously with those line halves, those half lines coming out to make the V and going each of the two directions. Now, obviously, that is not the only change that we can make. And for the sake of conversation, I'm going to put the A back to 1. We know that we can adjust the slope with the A, and we know that we can adjust the direction. H. H has the option of moving you left and right. H slides the graph left and right. The most difficult thing for people to do with H is to recognize that this general form already has a minus sign in it. And that is something to get used to as you progress throughout the year. You are going to see this a lot. When it is the interior argument of the function, you see that fairly regularly where you have to adjust based off of that being a negative. If I go to the right and I increase my H so that it's positive, I'm going to move to the right and all the way back to the left, and I can slide my graph to the left. But again, remembering that the general form has the minus sign in it. Lastly, we're looking at the K. The K has a plus in front of it. Positive values of K move us up. Negative values of K move us down. Not changing the shape, which is what we hope. We don't want the shape to be changed in all kinds of different places. We want there to be dedicated spots where the shape is going to change. The shape is usually the one that is the hardest to recognize and the hardest to deal with. So we want to make sure that's the one that's the easiest to recognize. The easiest to manipulate. And that's just that number that's on the outside of the absolute value. So just for the sake of conversation and clarification, let's create one and then see if our graph matches. So I'm going to make H equal to 3.1. We'll make K -4, and we'll make A -1.3. And when I graph my extra compound inequality, or I'm sorry, not compound inequality, absolute value function, when I start graphing it, you'll see that I'm starting to follow, as I go left or right as I'm typing, you'll see that I start to create different parts. So I put the absolute value in. Now I've got my upside down V. Now I'm going to put a -3.1. So now I'm centered over the top of that V that we created. And we finish with a -3.1 to move it down. And I'm right on top of where I was previously. So adjusting each one of those A, H, and K allows us to move this absolute value function as needed. And if you remember that H controls the rights and the lefts, K controls the ups and the downs, and A controls the steepness and the direction, you should have no problem applying this to any situation, regardless the complications and regardless the size of the numbers.